Hello, good morning everyone. Welcome to the second video on the simulation or the one concept, multiple tools, multiple learning series. And today's topic is about projectile motion. So let us begin this. Let me share my screen. Right. Okay. So projectile motion as such is one of the toughest topic for many of the students that we have observed so far. It could be in any curriculum. It could be in IB, IGCSE, ASA level, or any sort of curriculum. Okay, you observe that most of the students do not understand this, and they make lots of mistakes while solving some problems. And in fact, I cannot say that doing an simulation of this sort will help them out. Okay, because the first primary thing that we need to know about is about understanding about the two-dimensional motion. Okay, how different is two-dimensional motion from one-dimensional motion? And if there is a two dimension, then that two dimension is equal to one dimension along the x-axis plus one dimension along the y-axis, and they can write independently the equations of motion, and finally they will be able to merge them making use of the time parameter. But what is important here is that to appreciate the what you call the two-dimensional motion, I felt that the kind of questions they should be asking here should be important. So why the topic on projectile motion becomes very difficult for the students is that initially when we start teaching the topic, we always teach them, okay, the three different ways of solving. That is, what is the value of range, what is the value of the maximum height, what is the time of flight, and so on. But when it comes to examination, especially in IB, we don't ask that kind of questions. We do not ask direct questions, but there will be some twist over there. The twist could be something like the context would be different, or maybe there could be a graphical question. And when it comes to a graphical question, student definitely fail into it. Okay, 99% of the students will have a problem. So towards it, I thought, okay, so why not we look at simulations and help them out to know about how to solve problems in this. What kind of context will we have? Because when we look at simulations, different developers will have different context. You would have designed things in a different way. Okay, one of them could have designed something like this. I can show it to you here. Okay, one has designed something like a normal projectile motion where he throws a particle and it lands at one point and he finds out what is the distance, what is the time taken, and so on. Okay, so one way. The other way, for example, here, if you look at this simulation here, you see, so there's a cliff here, and on the top of a cliff, you have a launcher, and this launcher is now sending out, or maybe throwing out, or ejecting out the particles, and as a result of it, it falls at different points. So this could be the second one. The third one could be something else. Okay, we want to find out like which are the particles may have the same initial speed, same maximum height. How does the angle of projection changes? Now, what we are doing is we are actually not designing solutions, but instead we are trying to ask newer questions over here. So that is what we are going to do. So what kind of questions can be asked in projectile motion? Okay, we always say, like if you know the enemy properly, then definitely will be able to target him correctly, right? So now we are now looking at what possible types of enemies can we get. Okay, so without wasting our time, let us continue with this, right? So projectile motion, it's nothing but a two-dimensional motion. Now this particular simulation tells you about something like what is the maximum height and what is the range. Now you can change some parameters. What are the parameters you can change? Let me change it over here. Just a minute. Right. Okay. So what is that we can change over here? We can change the initial velocity and we can change the angle of projection over here. So that once I change any one of them, I would be able to find out what is the maximum height reached by the particle, what is the maximum distance by the particle. Now, how do I teach to my students? What I should do is how I do it is something like I put the simulation onto the board, and then what I do is I show them, okay, this is what it is happening, and I change these values, and they already have the equations. They can calculate this, they can use these equations, calculate the value of it, and then similarly look at the same values whether they're getting it or not, and thus they will be able to cross check it. That's one way of looking at it. So therefore, now let us say, for example, if I change the initial angle here, as I change the initial angle, and then okay, so it's here. Just give me a moment. This is blocking my view. Just keep it somewhere. It's here. Okay. So now what I do is, let me first clear everything over here, and let me start with this. So initially I can keep, like for example, I can keep it at 10 degrees or something. I can click here and type 10 degrees, and the initial velocity of projection is 50. Fire it. So it falls in some place over here. I can find out what is the distance over here, and then I can change the angle. Maybe I'll change it to 20, 20. And as a result of it, once again, if I fire, I get a much larger angle. Now, as I keep on changing this angle, okay, we usually expect that the distance or the range that is being followed should become higher and higher, right? So if it's 30 over here, let me take 40, press enter, click on fire. So you get around 250 meters over here. Now the question that we can ask is, okay, this could also be something like an initial hypothesis testing, or maybe we can use this as something like a introduction to your IA or EE, IA especially, not EE. So we can ask them like, how do you derive a hypothesis of it? What could be your independent variable? What could be a dependent variable? What are the control variables? We can look at all these things. Okay, so usually if the student is able to understand how to start with an IA, how to coin the problem, how to get the variables, then definitely I think you'll be able to do very well in this IA. Okay, now here comes the difference. Let us say, for example, if I make it 50 over here, and then I click on fire, now I observe that the distance is almost the same over here, or it is equal exactly over here. So if I keep on changing like this, and I observe that the range will now change, right? The range is staying over here. Now we can ask a question over here. See, this yellow line and this blue line are seem to be overlapping with each other. Okay, so not overlapping, that means the ranges are one and the same, though the path taken is different. Okay, what is the pattern that you observe over here? The pattern, we can say this one was done for, let me take up this value. This one was done for how much? What's the angle here? This was done for 50, and this was 10, this was 20, this was 30. I think this is 30, right? This is 30, and what is this now? This is 60. 30 and 60 over here. For angles of 30 and 60 observed, you get the same range. In a similar way, if I take this one, this was done for 30 and this was done for 40. This was done for 40 and this was 50. 40 and 50, once again I get the same range. Now we can ask the question, is it that there is a pattern which tells you that the sum of the two angles of projection, what are sum of two angles of projection? 40 plus 50, which is 90 here. Similarly, here it is 30 plus 60, which is 90 here. Okay, for some of the angles of projection equal to 90 degrees, the range appears to be the same. The range is same. Okay, can we put across a hypothesis like this? And how do you prove it? Now you see, I have arrived at a mathematics. I have looked at, okay, how do you prove something? Okay, so this invokes the thinking skills, right? So this is what your critical thinking skills will be present over here. So this we can do it. Now, the next kind of questions that I can ask using this simulation is that, now let us say in all these cases, you observe that there is symmetricity being seen. Okay, the curve is highly symmetric. Now, how do I make it unsymmetric, asymmetric? So how do I make it asymmetric? For example, there is something called as air resistance over here. Now I can pull this one here, air resistance here. I can pull this one here 0 to 0.02. I'll make it a little bit higher. I'll make it as 4.6. Okay, which is given by some parameter b by m, which is not there in their syllabus, but at least it will help them to understand that there's some air resistance over here. Okay, let me fire this at the same 60 degrees. The same 60 degrees, I get it over here, right? Maybe it is not clear. What I will do is, this was an MCQ problem. I'll show you what we can do. I'll just clear this whole thing. First, I will do it at, let us say, initial angle to be around 30 degrees, and keep this one here and make this one to be 0. Make this one to be 0. That means no air resistance. Now you get a symmetric curve as shown. Next, what I will do is, I will introduce a air resistance, the same 30 degrees, and I will introduce an air resistance of, let us say, 1. Don't worry what is the unit over here. We'll just say air resistance over here. Keep it as 1, and then let me fire this. Now what do I see here? I see that the peaks have been shifted. So this is the question we need to ask. what is the peak over here? The peak here was around 118, and the peak here is seen to be 99.3, which means the maximum height has lowered down, and you see the range has also been shifted down, right? It's been shifted over here. Okay, which means now if this is where is it? Is the symmetricity being preserved? That's a question we need to ask. Let's say if this is 100 and you look at this here, you look at this point over here, this is around 190. Where you should expect the symmetric point, where should the midpoint be? Midpoint should be, if this is around 190 or 192, midpoint should be around 96. Okay, do I get it at 96? Let us ask this question. 95.4 is here, 96 is somewhere here, 96.9 somewhere over here. Okay, but still, this, as you look at a visual characteristics, you don't see the midpoint over here. Maybe if I increase this, okay, that'll be very clear. It'll be completely a skewed distribution. Now let us make it as something like 5 over here. 5 over here. Okay, and then let me click on this fire once again. I get it over here. Okay, so now you see what was the range here. This was around 221, and the midpoint of this when it was 0 was seen to be around what is it, 221 is 111 or something, 110.5 you should get somewhere at this point. You're getting it here. Now here you see the end point is 131 here, and you should be getting around 65 over here. Where is 65? 65 is somewhere over here. 63 is 65. 65 is here. Is that the midpoint? That is not the midpoint, right? It's completely skewed, right? So therefore, three things that we have observed. First is the max height reduces. Second one is you can see that the distance, the range, okay, will also reduce. Both these are obvious for us. Okay, and the last one is we see that the distribution of the points over here, okay, is not the same. It is different. If this is different, what else can change? The time taken for the uptime. The uptime might be higher. The downtime might be, uptime might be lower and the downtime might be higher. Something like this also you can understand. But we don't have any idea about how to test that one. Okay, which maybe when we go for the next few simulations, you will be able to look at it. At least it gives you an idea of what to look into, right? This is very important. Okay, now let us move on to the next one. The what you call the URL for this is already made available to you in the description. You can look into it. Okay, let us go on to the next one. Now let me clear this first before we start this. Okay, now I have something like a launcher, maybe something like a cricket ball launcher, or maybe okay, any other type of launcher, a ball launcher, for example, is kept here, and I can change this angle. See, I can change this angle like this. I can change this angle here. I can keep it like this. What is the angle here? 60 degrees over here. I can put it down over here. What's the angle here? Minus 45. How do I know? So it's given here, minus 45 over here, and the height is kept at 8 meters. I will not be able to change. Will I be able to change? Wow, I am able to change the height also. I can change the height also. Okay, I'll keep the height over here at 10 meters, and I can change the speed. I can also change the gravity. Okay, I can change anything over here. Okay, now what I do is, let me keep it over here. Now the question I can ask is that when I launch a projectile from here, will it undergo a straight line like this, right? Let me launch it at this point. What do you observe? It doesn't go a straight line, but instead it gives rise to a curved path over here. So why does it give a curved path? That's the question we need to ask, right? Now, if I increase this speed, if I decrease the speed, let us say I keep it at 23 meters per second, and now repeat the same one. Now you see the curve is very clearly seen. Now the question we can ask is, if I increase the speed or decrease the speed, at what moment can you see that this will become a straight line, right? If I increase the speed, I keep it like this, 100 meters per second. It almost appears to be a straight line, right? Which means velocity increases, then it becomes straight line. Now I can ask my student to say that, okay, so take up the data from this, okay, for different values of the speed, what is the ranges where you get? Okay, just take the starting point here. Okay, let us say this x point is equal to 0, y point is equal to, this x point over here, you get something here. And then I can ask them to plot a graph of this and explain me, okay, whether in which line, in which of these angles will you get a straight line trajectory, and justify why do you think so, right? So this is something, okay, from the graphical point of view also they will understand. They need to find out the slope over there. Once they find the slope, okay, for every point, for every angle, for example, I'll just show you now. For let us say, for example, I have done it for, I'll do one by one. So I'll keep it at, let me clear this first as an example. I'll keep this exactly at, can I change it here? I can't change here. Okay, so I'll keep it at 11 meters per second initially. I'll launch it. Okay, what is the distance? Where does it land over here? Displacement is 52 meters. 52 meters over here. Okay, then vertical is 262 meters. What is the vertical displacement over here? Horizontal line. I'll take up this. I do not know what you mean by vertical here, because we already taken vertical to be at a height of 10 meters. So this doesn't make any sense. Okay, let us do this one here. So this we have got. And now let me change this angle. Minus 45 we are done. So for a given angle, then 11 meters per second we have done. Now let me do it as 21. I'm not able to keep it. Okay, let me do it 23. Okay, so now if this is 52 and this was 0 over here, 52 minus 0 divided by this height. Okay, I'll get the slope over. Right. And what is this velocity here? Velocity at 8 meter per second. The horizontal velocity is 8 meter per second. Vertical velocity is 72 meter per second. Why does this increase? You can ask these kinds of questions, right? It increases. The reason is because the velocity, vertical component of velocity is acted upon, or it has been accelerated by the component of gravity, and hence it increases. Now I will increase this. I'll make it 23 meter per second. I'll launch it once again. Now I get this value. So the displacement here is 92, and this was here at 0. So therefore, I get this horizontal distance. What is this now? 92 minus 0. What is the height? I already know the height over here. So if I divide this by this, I get the slope. Okay, I get some average value of slope. It's not the exact value, it's some average value I'll get. Now, what do you think about this slope and this slope? See, this slope, okay, is differing over here, of course. Okay, but you see at different points, I can take the slope and I can get the answer. Or maybe I'll get some value of the slope here. Okay, now let us find out. This is more steeper, this is less steeper, right? Now let me increase this angle. 26, 28. I have to keep it at 35. Okay. Now once again, I get a different slope. So like this, if I keep on calculating the slope at one point of time, okay, so I'll see that the slope at every point will be the same. And as a result of it, I can define that this one is seen to be a straight line. Okay, the path is seen to be a straight line. So this is one of the way to prove that. Okay, so these kinds of questions can also be asked. Now let me take up the next one. Now here, now this is summarizing thing. Okay, so what does it tell you? This is from O physics. It tells you about, let me reset this first. Let me reset this. Now the question is that if I fire the projectile in such a way, okay, that all of them will have the same initial speed. Okay, for different angles of projection. What is this now here? In the simulation, you can look at the path of the 4 projectiles all shot over ground. Projectiles are launched at different angles, 20, 30, 45, and 60. 4 different angles you have. You can choose whether you want to have them all the horizontal range, okay, or the same maximum height, same initial velocity. This is summarizing part. Okay, so what you can do is, let us say this is your angle of projection, and this is your, what is on the y-axis? I think it is the same velocity. Let me just check it out. If I fire here, give him the same initial speed. With the same initial speed, this is taking some time because I have put so many browsers been open. Okay, it's going on here, right? So this is at 25, this is at 40. What was the angles being given? 20, 30, 45, and 60. 20, 30, 45, and 60. Okay, so when I launch it at different angles over here, and I observe the maximum height and the range over here. This is what is being shown. The range is seen to be highest for this one, or maybe much more higher for, I think for this, or this would be higher. For 60, 45 would be higher, then 30, then you get 25, and so on. And this would be lower one. Okay, so for the same, what do you call it, if you launch a projectile with the same initial speed, but different angles of projection, then how will it look like? Okay, the trajectory of the paths that is being seen can be understood from here. So you can also see something like a same maximum height. Let me pass this. You can pass this. Oh, it's my browser is very slow. The reason is because I have opened so many. You can try it at your place. Okay, so this is how you would be able to run this and ask such kinds of questions. We can ask them to derive, okay, do you get the same result mathematically also? What is that you do if you want to get mathematically the same thing? Okay, you can do this. Then next comes this. This is nothing but a projectile motion calculator. So what does this projectile motion calculator do? Opening something else over here. Okay, no problem. Okay, so What you can do is, say it does not give you any simulation over here, you can actually substitute the values of initial velocity, angle of launch, initial height. Okay, you can find out, okay, any of the parameter making use of this. Let me just give you some initial parameters and I ask you, okay, I can find out the initial velocity components, and I can share that. I can reload, I can just find out, okay, so what is that we get from here. Okay, so based on the type of problems that you have, you can use this one here. There's a video which shows, okay, how to use this one here. You can look into this also. Next one, this site will give you, is about physicsprep.com. This site gives you a few of the questions which can be acted as which can be used as an activity, wherein if you are struggling to give an activity for the students to start with, then what you can do is you can copy these questions and you can give it to them and ask them to do the same activity using any one of these tools that we have. So see to it that it is been supporting, and then ask them to jot out the answers completely, write down the answers as a worksheet, and then you can use it to understand their to look at their understanding about the projectile motion. So this is what it gives you. So of course he has used PHET throughout my video series here. I'm not using PHET because most of us use PHET. There's no point in me describing PHET once again. So without PHET, what are all the other tools we have? I'm just looking at it. PHET gives you a number of simulations. Okay, you can use that also. Doesn't matter. Okay, if you are happy with PHET, you can do it. But this is only about, okay, what extra you can do about using the other tools. Right. Next one. This one. So this is very similar to the O physics tool that we have seen over here. But only thing is it's more smoother, and it gives you, okay, about the y versus x, okay, and x versus angles. For example, you can change over here. Okay, the value of g also you can change. There you can't change the value of g. Here you can change the value of g, you can change the value of velocity, you can do all these things and plot respectively, okay, individual graphs. For example, if I want to have maximum heights, okay, and then I click on this play button over here, I get something like this. So what does this tell you? It tells you about different angles of projection. For different angles of projection, where does the particle actually land over here? Okay, and it also gives you the time taken. Okay, so it gives you the y versus x over here, and maximum x is equal to how much, and what is the maximum t over here. This is only for this x over here, and the value of g I have used is around 10 meters per second, and the maximum height it has reached is around 45 meters. And this also gives you one more. Okay, this graph one is to interpret maximum height versus angle. Okay, as the angle changes, what is the maximum height? It changes over here. You will be able to write it. Similarly, time of flight. Okay, for different angles of projection. Which angles of projection? 0, 10, 15, 20, and so on, 15, 30, 45, and so on. When I click on this play over here, you see, this is how the total time changes with the angle of projection. Okay, so as you see, this is not a straight line. It goes a straight line a little bit, and therefore it keeps on deviating, and it almost remains a constant over here. And then the distance of displacement is the same thing what we have seen earlier also. In fact, what you can still do it here is that you can change the value of g here. Let me take, for example, I take a very less value of g. I take it like this over here, and I want to find, let us say, horizontal distance. This horizontal distance and this horizontal distance we already have here. I'll do one thing. Okay, let me use this anyway. Okay, I'll click on this because we have not used it. Now, what do you observe here? So for y versus x, that is the maximum height versus the horizontal ranges, you observe that this will go straight, and this is how the variation looks like. Almost it looks the same one. Okay, but what will take is, okay, this will take a very longer time to actually come back downwards. Okay, this one. Okay, but this all will come faster. Okay, you see, this is taking a very longer time. Right, and now let us look at this one here. X distance versus angle. So in the previous cases, you observe that the plot was something like it was going straight and it was coming downwards. So here, now you see, okay, I'm sorry, I made a mistake over here. We haven't seen that. Okay, just a minute. So the maximum height reaches 225 meters, and the horizontal distance is for the angle versus the distance which is being given. So it has been shown over here. If I now change the value of g, I'm also curious, I have not tried this. Okay, if I change the angle over here and click on play, of course you get the same kind of curve. I thought maybe you get a different one. You get the same kind of curve over here. Okay, so you get the same one, but the only thing is the distance traveled by it would be lesser. Distance by traveled would be lesser. Don't take this as maximum height. Okay, this is what our students actually do it. Okay, when they plot a graph, they assume that this is your Horizontal distance, not horizontal distance. We should first show them what kind of graphs do we have, and how do you actually interpret that. So this is your degrees and this is your distance over here. Okay, now let me move on to the next one. Now this is really amusing. So what it tells you is that on Earth, okay, so you have something like a projectile, a launcher, and you are launching it at a, you're not able to change this one here, the same angle, that is horizontally. And from here, when you launch, then what will happen to a different velocities? Let us say I launch it at 1 meter per second. Where does it fall? It falls at a nearby place. At 2 meter per second, it falls at a much farther place. Sorry, not 1 meter, it's 1 kilometer. Sorry, 1 kilometer, 3 kilometer per second, it falls at this point. What you can do is, I'm not able to change this. Okay, if you are a good developer, if you have any students in your CSE, computer science, and if they are willing to do something like a project under you, you can ask them to do two things. The first one is you can have an earth and you can make it to rotate. When you rotate, what happens is the launcher is also rotating at some angular velocity. And as a result of it, if you do not keep it over here, you keep it at some other point, you do not keep it at the poles over here, okay, at the axis of it. And then what happens is they say Coriolis force also acts. So it will fall, okay, at what location you'll be able to do it. So you need not do something like what you call a simulation like this. You can also design a spreadsheet. Okay, it will be a wonderful thing to do. If possible, I will try to do it over here, okay, and put it across in my website. Otherwise, you can also do the same thing over there. Okay, so this you can see a 3 kilometer per second, it falls over here. Okay, that means if you're standing at one point and from there you are throwing, okay, where does the projectile go and fall? Okay, and which country does it fall? You can ask this question. At 4 kilometer per second, it falls at much more farther point. At 5, still higher. 6, still keeps on going like this. At 7, you see, this goes and falls over here. Okay, see, almost it is for 50% of the globe, okay, it is not touching anywhere over here. Okay, now let me take it as the next one. I will take this one here and put it over here. Okay, at 7.9. Now what's happening? At 7.9, it is just orbiting around it. That means it never touches the Earth, right? So, and then when I go to 9, what's happening? So it is still orbiting around the Earth, but it is going at a speed of, at a very high speed, and hence it doesn't show a circular path, it shows an elliptical path over here. If I go to 10 kilometer per second, let me click on this, 10 kilometer per second, what happens? The elliptical path increases, the semi-major axis keeps on increasing. So this is what you can see. Now when I go to 11.2 kilometer per second, what happens? The particle never returns back, right? What is 11.2? Escape velocity. From where to where we have linked? We have linked from the kinematics, which was in projectile motion, and we have directly gone to gravitation. Okay, so this is how, okay, one has to link. This is how I usually use link, okay, when I do a projectile motion study. Okay, and then let me move on to the next one. This particular animation is a really wonderful simulation thing. Okay, try it out in your classes. People will really appreciate. Okay, that means when you are teaching something in your first chapter itself, okay, you are giving a cross reference to the other chapters. When you go to that chapter, you can always come back and say, okay, hey, this is what I had done earlier, and you can understand, okay, how does this work. So you are not studying, you are not asking the student to study chapters independently. Okay, it's not like you study chapter 1, and when you go to chapter 5, you are not saying, okay, chapter 5 is different from chapter 1. Chapter 5 and chapter 1 are seen to be linked. So you get a holistic view of all the chapters. So given any applicational problem, you should be able to start solving that in a much more easier way. Right? This is how it helps you. Okay. Then coming back to the parameters, they definitely need to work on it. But doing simulations, they definitely get to understand how to link one chapter to the other chapter, because it is both you are doing it and it's also visually appealing. This is where it helps you out. So somewhere I feel visual experiments are very much important while we teach for the IB curriculum or for any other curriculum. Let me go to the next one. Now, what is this about? This is not there in our syllabus, okay? But it's important for us to teach these kinds of questions also. Because tomorrow, if they are doing an IA or E, then these kinds of animations, simulations will be very useful for them. So what it does is that you have a beaker filled with water, and there's a small hole over here, okay? And then what you do is, if you click on this, what happens? As the water level keeps on lowering, then the water now starts flowing from one end to the other. Okay, so it describes a projectile motion over here. Okay, that's what it tells you. And in fact, you can find out what is the velocity of the flow. You can find out what is the parabolic equation it does. You can do all these things over here. Okay, now what we'll do is, let me see. Let me decrease something over here. What I'll do is, I'll decrease this. See, there's an arrow here. I'll decrease this. Am I able to do this? Oh, I'm not able to do anything over here. I thought I can change something over here. Okay, or maybe I have to reset this first. First, let me reset this, and then, and I'm not able to do this. Oh, I'm sorry. I was able to do it yesterday or something, but okay. So this is what we can do it. But in fact, if there were some tools, not able to see any tools over here. If there were any tools, just a minute, just a minute, wait. Oh, these are static values. I'm not able to do anything. Okay, so if there were anything related to fluid dynamics, then please do trying doing this also. Okay, as the water level decreases, okay, where does this pot of water fall? So here initially you can do this, or maybe you can also think about doing this as an idea also. Okay, let me go on to the next. Okay, now, so what does this tell you? There's a spring here, there's a set of banana over here, there's a chimpanzee setting over here. Okay, and then will I be able to change? I'm able to change. This is not a seesaw over here. This is only something like I'm able to change this. When I change this over here, what do you observe? There's a compression on the spring. When I bring it nearby here, there's an expansion over the spring. So how does it change? Does it change the spring constant? Okay, it doesn't change the spring constant, but what it does is the velocity of the bananas will increase. See, for example, when I am bringing the slider here, you observe the velocity seems to be 15 meter per second. When I bring it here, 25, 26, 27, 31, 35, 45, 53, see, it keeps on increasing, which means what? The velocity of the banana at the time of release is seen to be higher. It's like this. Now, this is nothing but a gamified version. Okay. So now, when I do something like this, and when I release it over here, the release is done by this button. Okay. When you click on this button at 245, this is the height is given here. 82 meters per second is the velocity. What do you think that the bananas will it exactly come and hit the chimpanzee or not? Let us try this. Now, there are two things that you need to measure. You need to look into it. The first one is the bananas went far away. Okay, and second one is there's one more set of banana which is being dropped. Okay, so two things are being done. Now the y component of the time taken by the bananas to start from there and to reach nearby to the ground in this direction or in this direction is one and the same. This is what you can show. Okay, let me do one thing. Let me reset this. Let me do this for a much lesser value. Let me do it for a much lesser value. Let me keep it over here. Okay, so how much is this? Around 57 meter per second. Let me click on the green button once again. Now, where does it fall? Yes, it's falling here. Yeah. It's coming down nearby to, wow, it hit it across. Right? Now, what did you observe here? The time taken by this banana, the time taken by this set of banana, when it falls over here, is seen to be the same time. Okay, it seems to be same time. So that means the time of fall does not depend upon the horizontal velocity. It only depends upon the height of where the object is being placed. Okay, that's what we can understand from here. Okay, so this can be given as a gamified version to make this understand. There are several examples. Most of the examples which I'm doing here would be very much related to this. I'm just showing you all of them. Then let me go on to the next one. Right. Now again here, now you see there's a spring, and on the spring, top of a spring, there's a banana which has been loaded. There's a truck kept over here. Okay, and then the velocity of this could be adjusted, but anyway, I'm not changing anything over here. Let me click on this green button. So what do you expect? When you click on this green button, then what can happen is the spring that you see here will get compressed, and the banana will be ejected from here, and it will reach here, and the truck will also move in this direction. When the truck moves in this direction, you should expect the banana should also move like this along with it, but it doesn't move because when the truck moves, the spring is automatically releasing this. The bananas will not have any horizontal velocity. It will not describe a projectile motion. That is what you need to understand. Okay, this is now given to show how the projectile motion acts. Okay, projectile motion acts when you have an object in contact with something and the horizontal velocity is added onto it when it is in contact. When it has left the contact and then the horizontal velocity is there, then there's no impact on it. Okay, that's what it does. Let me click on this. Now, as it goes upwards, you see, it is just going vertically upwards. Okay, it is not doing anything else. So it is not moving in a horizontal one. So though the truck has moved downwards, right? So this is what we need to understand. In fact, if you had watched some of the Instagram reels, I think long back, not now, maybe 2-3 years before, I watched something like a person at bikers, two bikers. Okay, don't. I urge the students not to do this one here. So what they do is they are moving in a vehicle, and when he approaches something like a lorry or something, one of the fellow jumps across. Okay, and no, it's not a lorry, I think. Okay, one of the fellow jumps, and after some moment of time, he comes and lands onto the same vehicle. So something which you have seen. Okay, and now this is also a very similar one. Let me move on to the next one. Okay, so this one is about, okay, a person who is moving in an aeroplane or a jet, and then he is now releasing a missile from here. There is a missile. Missile is being released from here, and it should hit the target. Okay. Now what you can do is you can ask the student to change. Okay, we are not changing anything. Okay, we'll continue here. Okay. Now what we can do is we can click here. Now as he is moving over here. Okay. Now you can decide. Okay. So this is a target to be hit. Now how much should be there? So if I play over here, if I play here, the person straight away moves over here, but the missile comes and hits it exactly over here. The horizontal velocity remains the same. Okay, let me run this once again. Reset this. Now click on this, and I have this higher values. How do I reduce these values? If I reduce these values, I'd be able to show, okay, how the horizontal velocity of this person and the missile remains a constant. So I'm not able to reduce anything over here. Okay, let me show it here. S equal to 20 meters, H naught equal to 5 meters, V naught equal to 20 meter per second. Oh, I'm sorry. The velocities are different. That doesn't happen. My prediction was wrong. Okay, see, the velocity of this shuttle, of this jet, is seen to be 72 kilometer per hour, while the velocity of the missile was seen to be 20 meter per second. And as a result of it, when it fires here, the jet moves faster. Okay, I can change it here. What I want to do is, I want to keep the velocities of both of them to be the same. Not able to do it. Okay, let me click on this. See, the jet moves faster while this comes after some time, and this hits over here. So this is just a gamified version of running the simulation. Okay, let me move on to the next one. This is quite interesting. So this tells you about, do I clear here? I have a reset button here. A monkey which is hanging from a coconut tree, many of you would have done this experiment. This is from more physics. Okay, and then you have to choose the firing, the angle of the firing in such a way that it goes and exactly hits the monkey. Okay, so how do you choose it is a question. Okay, so there are sliders which are being given here, velocities, you keep all of them to be a constant. Now what you do is, let me fix this angle somewhere over here. Okay, this could be useful, wonderful game for the students to work with. Okay, and then now when I fire here, do you think this will hit or not? Okay, when you click here, you see, it moves farther away, right? So it never clicks over there. Okay, now what I will do is, let me reset this once again, and let me change the angle. Let me keep it at, it says too low, right? If I keep it at 21.4 degrees and fire, you see, it appears to me, no, it missed it. It's once again too low. Even now also, it did not fire. Okay, let me reset this. It's really wonderful to play such kinds of games. Let me exactly point it to its tail. If I point it to its tail, do you think it will hit? I don't think so. Okay, let me point it to its somewhere over here. Okay, to its arms. Okay, now let me fire here. No, it still missed it. Okay, now let me reset it once again. Let me change this angle a little bit more. I'll increase it to exactly at its head. And now fire it. See, this is what you need to look at. Okay, the red color bullet. I'm not looking at the green angle over here. That is your initial velocity. Still, it was too low. Okay, what we do is, let me reset this. Let me change the angle. So somewhere 27.8. Now look at this red dot. Exactly. It's almost hit it. So like this, okay, so you can ask the students to do this one and see how does it work. You can ask them to change the initial velocity. You can ask them to change this value also. Say for example, y naught value, I can change this also. I can change this also. Some students might think if I am at the same height, I will be able to do it. Okay, let me keep it over here, doesn't matter. And I'll change the angle. So how much will I change the angle? I'll change the angle here like this. I can keep it only at 0. Oh my god, by the time it comes down, this is not possible. So what I'll do is I'll reduce the angle also. I already reduced the angle. I'll change this height also. I'll change this height. So it is so tempting for us itself to play this, right? Okay, now let us fire this and see whether we are able to do it. No, see the bullet fell over here, right? So we are not able to do it. Okay, so like this, okay, you can also ask the students to play with it to get, okay, at what appropriate angles and what appropriate theta values, okay, you would be able to find it, right? So they can come out with something like a data collection, and then they can do a graphical analysis. So many things you can do with using this, right? Okay, let me move on to the next one. There are two more. This one, I really find it amusing. Okay, so you have a target. What I can do is I can change the target here. Now the target is being kept over here, and then I can click on the new target. See, this is randomly it has been selected. Okay. See, every time when I can click on this one here, this blue button, new target over here, I can change it randomly. I can change it over here. Let me show you where is the new target over here. New target is somewhere over here. New target is here. Now I should change the values of theta and velocity so it goes and hits. I need to make a guess. What is the guess over here? So what I will do is, see, this is shown for 53 degrees. It hits over here. Let me change this to, because I know 45 degrees is, okay, it gives you a maximum range. I will keep this at, see, if I assume, if I threw from here and it fell over here, this could be 45, this could be around 40. Let me keep it as 40, 45, 43, 42, 40, 38, 39. Okay, let me keep it at 40. And let me keep this at 80 units only. Let me throw. Oh my god, no, it doesn't go there. And maybe I have to change this value. I'll keep it at 90. When I do this, once again, slow a little bit away. Okay, now maybe I'll change this projection angles a little bit. 40, 41, 42. No. Oh, concentric. No. Okay, let me increase this velocity also. This I play it often. Okay, so next. Wow. Aha. So we have come nearby to it. Let me reduce it to 96 at 42 degrees and 96 meter per second. Yes. I got it, right? So these kinds of things also one can start playing with this. So we always keep on complaining, our students keep on using lots of what you call e-content, they use lots of digital media and so on. But if at all, if we are able to supplement, okay, the digital media in this way, then learning also gets supplemented along with it. Okay, you will need not complain. You can always say, keep on using digital media and keep on using simulations, learn more about the physics, right? So you should make physics, okay, more interesting. Okay, if you start making physics more interesting by using any one of these what you call tools, then definitely it will be students will get hooked to it. Okay, let me move on to the last one. This is very similar to that one, again a gamified version. Okay, so what you can do once again here is that the only advantage of doing this one here is that you can choose any one of them. Okay, a monkey and the hunter, man shoots apple, user defined also you can do it. I don't have anything which is user defined over here. Maybe I can choose this. I can choose this launch angle over here. Okay, let me try playing this. I have not tried this. Yesterday I was searching for it and I got this one here. No, it's not showing up. Okay, maybe I have to reset this. I have to reset this. Man shoots the apple. It's like this. I can play with this also. Right. Okay. So like this, There are several tools that we have, okay, to use for projectile motion. Of course, projectile motion is something which one needs to work it out to understand this. But in order to inculcate that interest in the students, so definitely I felt um, doing simulations or doing some gamified versions of this would be really useful. So if you find this video to be interesting, not boring, then do subscribe to my channel, share this with your friends, your students, and please try it out in your schools and let me know in your feedback in the comment sections below in the video, like how useful was this. Okay, so that I can understand, I can get to know, okay, how such kinds of things will also be useful. Because I do try in my school also, like how to go with it. But I would generally like to know, larger a cohort, and definitely you get to know better understanding about, okay, how does it work. So with this, I would like to stop my lecture. Tomorrow, let me take up something on circular motion. I have not seen, okay, how many web aligned tools are available for it. Whatever is aligned, whatever is available, and I will just take up that particular concept and do it. So shortly, I'll be putting across these videos also into my website. I'm revamping my website totally. You know what is my website? It is ibphysicswithrao.com. So just go through it, and if you feel anything else has to be changed, definitely we'll do it. Currently, the support is only for IBDP. Maybe by next this October or November later on, I think I'll be starting even for the AS level also, and AS level will be completing it by next December. This December, not even December. I think, yeah, it might take until December. Only MCQs, not structured. And after that, I'm planning to start something, okay, which is suspense now. We'll do it definitely. I'll let you know. Okay, so until this, thank you. We'll see you tomorrow once again. Thank you very much.